Hey guys, how's it going? So back again for a little bit more of the Open-FDD vibe coding here. So I was going to try and do this all in Codex, just the normal Codex CLI, where I can use all of the ChatGPT agents that come with my ChatGPT subscription. But I just totally burned through uh, my 5 hour usage limit. So I'm just going to try and download this or try and do this with just through Cursor, just with my AI IDE, which is probably something I would use anyways. So if I was doing any of this professionally, I would probably exclusively just be using my AI IDE. So um, I'm just gonna put in, I have like one Cursor instance running here, and I have like this huge, this prompt. So I'm just gonna dump in this prompt. And then um, okay, so this is a big prompt created by Cursor that I am going to dump it into another instance of Cursor running on a different computer. So this is my Linux computer. Same thing that we've been doing a lot of having a lot of fun with in a Python BACnet Stacks playground. It's just a little tower I have like running right next to me. It's actually my old Windows computer that's now permanently switched over to just a Linux test box for my science experiments. And then this computer here that I'm recording this YouTube video on is like just a much more modern, powerful Windows computer, but this Linux box still has some, it still doesn't have a lot of RAM or anything like that. It has a terabyte of uh, solid state drive, and it's kind of good enough to run some experiments with. So it's running Ubuntu server. It's headless. There's no desktop environment. It's just we SSH into this only, kind of like a Raspberry Pi, but it's Ubuntu Linux. So we'll get into this a little bit later. So I'm just gonna hit this button right now. So there's Docker running on this machine. And while this crunches away, I'll explain to you what I'm hopefully going to try and do. So I have this buildings 100 and then other building 50 on Google Drive. And this is weather data from OpenMedio. So there's all these CSV files, the chiller running, the boilers, air handling units, and everything. Same building we've been working with prior. So then back in Stacks Playground, this is all part of this vibe code app 19. Um, so what's going on here? This is a Streamlit application now. So if we just go to Streamlit, let's just go to Streamlit. I can explain a little bit what's going on here. So Streamlit is just it's a data science application for analysts can use this. Now I can't even remember if I explained this very much on the last couple videos, but it's a dashboarding application. So get back. So Streamlit. Just get explore. So Streamlit is like it's a Python framework um, that you can use to make dashboards. It's meant for like data scientists, analysts, where you can spin up like a little HTTP, like a web app, but you don't have to be a full blown software engineer to do it. So there's a couple frameworks in Python you can do this. Streamlit is one very popular one. Dash is another really popular one by the Plotly um, Foundation. And I thought like there's another cool yeah. Anyways, Streamlit's cool. So like if you go to if you were an R programmer, not Python, the R programming language, which is really popular for statisticians. There's another dashboarding application called Shiny, I think, for the statisticians that use R. But we're just doing Python. So Vibecode app 19, this is it's here as a GitHub package as well. So this is just a Streamlit application, and it has an agents markdown file and also an agentic specification for software engineering. So like agentic AI software engineering spec. So like if someone wanted to, someone could basically just on their wherever they do their development work, they could just copy this link and then right in Vibecode app 19, they could just be, aim their AI agent here, and it would basically give it the it's a specification to how to recreate the app, make it your own. Or you can actually use what's on GitHub right here. It's packaged as its own Docker container. So this is kind of cool too. So like you can just go Docker pull right in Linux and Bash, and it'll pull this latest build of the project, which is in this prompt right here. So this is actually pulling the latest Docker container, and then this prompt is actually pulling the data from GitHub, or not from GitHub, from Google Drive. And then it's going to test the Streamlit application, preload it with the data, run all the fault detection. So it's kind of like a test that the AI agent can handle running all the fault detection equations. And it's basically is my little helper to um, prep the data if it needs prepping, clean the data, load the data, get the web app ready for me. And then I'm the human in the loop where then we can put on our mechanical engineering hats, and then we can actually go and look at the data. So let's just see where it's at. So it went through this really big prompt where it's downloading the downloading. So it's just, yeah, it's running crap. Now it's running into some kind of an error here. This has issues. Um, no, okay, it doesn't have issues. Let's open you in the browser. All right. All right. So now it's supposed to continue with that big prompt. Okay, so this is like what the Streamlit app is looking like so far. So Open-FDD Vibe Coder, and we tasked the agent to preload it for us. A couple little sidebar things here. We have web data that we can get from OpenMedia. So when we run analytics, that we have a fault rule that compares data from the web. So web weather data from a local weather station, compare that to the local building automation outside air temp sensors, which should be a higher quality sensor. Airport weather station compared to a local building automation sensor should be much better. Okay, so where are we going? Okay, so I think we discussed this already on Open-FDD. In the docs. The the cookbook, the pandas cookbook. So this is running there's 50 fault equations that are running in the Streamlit app. So there's Python code buried behind the scenes here. So we'll look at this. I don't think I'll have enough time today. I'm kind of on a little bit of a time crunch, but we'll look at all of these fault equations running behind the scenes. Let's just see where we're at here. So it looks like it's still. Okay, so it's running like some checks. I'm able to log into it. So it's this other cursor instance, which is here. This prompt that I copied over, I think it had it run a bunch of things. So it's BACnet playground. I think let's zoom in on this. So this is the prompt that it ran. BACnet playground, the latest GitHub, the GitHub container repository image for Vibe 19. What did it tell it to do? Okay, so then we told it to get Docker pull it, run it. So it's doing some agent checks. Okay, so like it's gonna do all the data modeling for us in a prompt, and then check for some kind of plotting error that I ran into earlier this morning. Yeah, and basically just it's basically running a test. So I do this all the time actually. I have like one cursor instance like software engineering, and then I have another instance doing the testing on a different computer, and then they prompt each other for where the bugs are. I kind of like it. It's not too much different than if there were humans, software engineers in the loop. We would have more than likely a professional software engineering testing person, and then there's also just the people, the web app software engineer themselves. So they go back and forth testing the application. Looks like there's some kind of things going on here. Let's go check it out. See what we got so far. These are all the fault rules. Then we'll be able to tune the fault rules. So this is the delay, startup delay, sensor tolerance for that fault, hit hunting fault, guideline 36 fault condition 1 for duct static pressure. These are all the guideline 36 fault equations. Weather station, couple economizer faults, and let's see, what do we got? How's it looking? So far, test complete. Live UI sidebar. The thing that's missing is we should see a bunch of analytics. So I'm just going to ask the agent to preload. So you can also load the data yourself. Data downloaded from Drive. Whether you can see it. So like what I'm shooting for here is that the AI agent can load the data. Oh, here it goes. Okay, so I'm dialing in to the Linux computer. This is like the standard little icon here that Streamlit has run. Kind of funny little thing. It looks like a triathlon. Okay, so what do we have here? Got some errors. Okay, so this is the same building. Date start March to July. This is where I can input the schedule for the building. So now we can start looking at some analytics. And now we have some piddly little bug here. That's expected. Okay. All right, so maybe I'll just have to think about this. How to get rid of this. There's some kind of an issue with the VAV box data. So that's why it's giving that just kind of like a warning. Okay, so like so we got this data loaded. The AI agent loaded the data for me, which is good. And let's just start looking at some analytics. So like, okay, so like this client said 6 a.m. to 1800, which is 5 p.m. So I think that's correct. And then on Sunday, we can do, there is an ability to do, this is really laggy. So 7 a.m. to slow here, but okay, so noon, 1, 2 o'clock, closed on Sunday. So this is part of their lease agreement to their clients, is they have to maintain 72-degree set point in the building from 6 to 5 Monday through Friday, then 7 to 2 only and then closed on Sunday. And then they can be saving energy. So like we're going to try and run some analytics that I'm going to crank this up, tighten this little dead band here. So I'm just going to do 70 to 75. So this is going to re-crunch. It's a lot of numbers here behind the scenes. So important thing, this is, you can switch between imperial and metric, but 70 to 75 is what I'm setting the application for, and bare minimum occupancy run hours is 67. So we should see that here. See this bare minimum line, this dashed line. And then, ooh, it looks like we're running it a little less than that even. Okay, so like what is this? So like what happens behind the scene is the AI agent does some data modeling. It's kind of a haystack naming convention, but it's not a full-blown haystack model. We'll get into more of the weeds of this in a little bit. I think this video is going to be kind of short just for today. But so what's going on behind the scenes is bare minimum run hours, and then like we're running more than this. This is degrees temperature outside in Fahrenheit. So in March, they're averaged about 40 degrees outside air temp on this axis over here. And then, getting into 50s, springtime. So this is like perfect economizing weather right here. In theory, we should be running bare minimum, especially when outside air temperature ranges are kind of like in the 50s. That's perfect. Free cooling. I don't know off the top of my head what that is in metric, but that is a 50-degree range. It's like perfect free cooling, which shouldn't be running a chiller then, or trying not to. And then as soon as we start getting up above 60 degrees Fahrenheit, that's typically when we start running mechanical cooling. So like what you could be seeing here is optimal start algorithms running if zone temperatures are requiring building to be up to temperature. What is interesting is either there's an algorithm on the BAS adjusting mechanical cool runtime, or there is optimal start, or there is the human building operator is doing things. So in June up here, that's when we start getting into mechanical cooling, and then we're this equipment is running longer than bare minimum, and this is the hardest algorithm to implement for energy saving purposes is this equipment runtime. This is classic the problem in the building. It should be the easiest low-hanging fruit to minimize equipment runtime, because these fans and chillers and electrical consuming equipment, that's like the direct correlation to electrical usage and power saving, reducing energy off your bill. Okay, so this is one ECM. What's cool about this application is this will populate automatically for each fan system in the building. The query is kind of programmatically driven by the data model. Okay, so boiler plant pumps, not bad. So this is typical. These are run hours per week. Same thing we saw up here, run hours per week. So pumping system, boiler pumps. And you can see there's some kind of, you can see in the data as outside air temperature gets warmer, that pump runtime is generally running, dropping off until June here, when we're averaging much warmer weather that it's almost off to nothing. Maybe there could be some optimizing in this, I don't know. But maybe in the next couple videos we'll get into looking at the BAS screenshots, and because sometimes you can see set points on there. Those are kind of classic indicators. I can also see here that for a variable volume air handling unit system, that they completely drop they must drop the boiler system. In theory, if this was a residential system, you'd never be running a boiler in the summer, but sometimes by design, I think VAV systems can require a boiler to be running even in the summer, and that's for dehumidification purposes. So like typically like what you would see is the building doesn't need heat anymore. The boiler system should shut off, and then there should be some time range during this economizing free cooling window right here that no heat is needed in the building and no reheat energy is needed in the building either for dehumidification purposes. So we only need heat like below 50 and then perhaps above 80. So there should be some time range in there where in theory you could shut the boilers off because we don't need to reheat for dehumidification purposes. And we don't need heat. I'm not really seeing that here, so I'll have to take a mental note that we could reduce our boiler usage. No, nothing for chiller. Okay, so this is an issue. I'll have to get the AI agent to publish this again, fix this. Because we should see another one for the chiller plan too. So I'm just gonna go. It's gonna plop this right into a cursor. Main dashboard. We should have a chiller 1 and chiller 2, and then go off of pump status, but I don't see a plot. But I do see one for this. Okay, so I'm gonna have the agent see if we can fix this. See this, which looks good. Please see if you can provide me the weekly run hour calcs for each chiller 1 and 2 via the Streamlit based off of their pump status tool. Okay, so like something's wrong. It'll make a plot kind of like this for the chiller 1 and 2, but what it did make is total mechanical cooling run hours per outside air temperature bins. So this is something that's kind of common in mechanical engineering theory, or they do calculations like this too for energy reduction, is what they do. If you see this outside air temperature, we can bin hours that the outside air temperature was this range, this range, this range, and this range. So it's this is a time series chart, but when we can bin how many hours the outside air temperature was between 45 and 50, how many hours the outside air temperature was between 50, 55, 55 to 60, 60 to 65, and so on. And then we can also, is the chiller running in those time frames too? So like we recorded 1.33 hours of runtime between 45 and 50, 36.5 hours between here, 100 hours of runtime between 55 and 60. So this is this right here would be data like when in theory we should be using free cooling by the air handling unit systems, and 60 and beyond we could do free cooling and free cooling and mechanical cooling up to a certain point, but 60 degrees and below, we should be trying not to run the chiller at all. So we can look into this. So I think this is all the time I have for today, guys, but let's do a deeper dive on this tomorrow. and then start taking some notes. Sorry, this has been going really slow, but what we'll get into is so all of the rules that we've ran. Some kind of issue where the um, we can run all the fault detection rules across the data model and then start going into the plots category. So let's start getting into this tomorrow. We can start start taking notes. Like we should be taking notes on reducing the chiller, reducing the air handling, or I'm sorry, reducing the air handling runtime, first of all, then reducing the chiller enable. That's another ECM. And, let's keep on compiling. We can basically compile like a nice list, and this could get sent off to the client and be like, these are the things wrong with the building that I've noticed. I have to actually run for today, but let's get back into this tomorrow, and then we can look at some BAS screenshots, and then even we can even look at another building, an identical building. So this is another kind of a twin building with similar systems. And then we can compare the two, I guess, and then maybe look a little bit of how the data modeling goes behind the scenes. But this is like what we'll get into is kind of looking at plots like this. And yeah, that's what we'll be doing. So thanks, guys. Thanks for following along. It's been a little bit slow going. I apologize for that, but it's coming along little by little. Talk to you later.